Morning, peeps. Ooh, sorry.
Morning.
How's everybody doing? So it snowed. We had all the weathers in Minnesota yesterday. We had sleet, we had hail, we had snow, and we had sunshine. Oh, and we had some rain. All in one day. It's like, yeah, Minnesota. Now it's just sort of gray and looking. There. Well, let's go ahead and start. It appears that as time has wandered on, attendance has dribbled a little bit, but of course, I know some people were probably working on the exam yesterday and have decided they've had enough of logic for the moment. So there's the last bit of chapter 3, the last bit of chapter 9. Oh, and I am recording. Yay, I'm recording. Apologies for Wednesday's mess up. Hopefully the replacement video, it was okay. I don't think it was probably as detailed as the original video would have been, but hopefully it did the job. So end of chapter 9 is Monday. I was going to do, oh man, get my notes here. I was going to do one more example from the end of that. And then I was going to be like done with those things. Unless there are questions. If there are questions, obviously be happy to do whatever of that would be helpful. So the example I was going to do was one of the 9.35 things. So actually, before I get to that, are there any questions about anything we've done so far? Any blah, blah, blah. Any questions about stuff? Going. Okay. Share the whiteboard. Oh, okay, there's something in chat going on. Okay. Cool. Thank you, sir. So I was going to do one of the 9.35 problems, a whole set of those. So actually, I quite like 934 and 935 are nice because if you're having trouble figuring out the issues of interleaving like a for all followed by an exists, or an exists followed by a for all, or a for all exists. If this, like, what's the difference between these is causing you trouble, like working through 934 and 935 is a great way to practice those. And you know, if you poke into those and you have questions, like you're like, I did all of 934 and I would like somebody to look at it and tell me if I did the right thing, I'd be happy to do that, if that would be helpful. You know, also, if you want to just make a little study group online, of course, because nobody can meet, but make a little study group and go through 935 as a group, and work something out. Like that would be, I think, really cool practice, and I would definitely recommend that. So I was going to do 935A, 935A, which says, so the 934s is like everybody loves somebody, somebody loves somebody, yada yada yada. 935 is about fooling people at various times. You can fool all the people some of the time. You can fool all of the people some of the time. You can't fool all the people all the time, etc. So A is you can't. Oh no, you can fool some of the people some of the time. Okay. Now, the first thing we're gonna have to figure out here is what are the what predicate or predicates plural are we going to need here? That's really the central opening question. And so the like thinking about the nouns in some sense. So, you know, predicates, if we think of something like registered SC, saying that student S has registered for course C. This is essentially a verb. Like it's an action that somebody took. Whereas these two things are essentially nouns. They're entities that were involved in the action. So in particular, this noun is the actor, the thing that does the acting, that took the action. Student S registered for, and this is an object, if we want to get into grammar land, which is not what this class is about, but this noun is the thing that was acted upon. So this student registered for this class, okay? So the name of the predicate is typically a verb, and the things that are passed in as arguments are typically nouns. And this is true generally in computer science. Like in this context, it's about logic, but it's also generally a useful thing to keep in mind when you're doing computer science stuff. If you're writing functions in programming, which is an awful lot of what programming is, the name of the function is often a verb because the function is an action that you can take. I want to look something up in the database. I want to update somebody's registration status. So those are actions that you take, and they correspond often to functions. So the names of functions are often verbs, and the arguments, the things that we pass in, are often nouns. They're the things that action is connected to, either the things taking the action or the things that the action is acting on, okay? So questions about that? I babbled on a lot there, but are there questions about the noun, verb, action thing? Okay. So then, like, what are the nouns and what are the verbs here? So if we have, so let's start with the verb. So what's the verb in this? What's the thing we are doing in this statement? Anybody?
Fooling people.
Yeah, we're fooling people, right? So the verb is some version of fool or to fool, or like we might want to change this name after we sort of work out some of the rest of it. But this is about fooling, okay? And then the nouns, what nouns are there that we're going to have to care about in this statement? Anybody?
People and time.
Yeah, it seems like people and time are the central thing. So some of the people, and I'm going to include the sum of the, because that might help us. When we get to the quantifier. And one thing that this suggests is that really at any given moment, we're worried about a person, right? If I say some of the people in the class have a nickel, when I'm checking that, like if I'm going around and verifying that, yes, some people have a nickel, I'm going to check it at the level of one person at a time. I'm going to be like, does Emma have a nickel? Does Blake have a nickel, right? So I'm going to have to ask the question about an individual person, but I'm ultimately having to, look at some of the people or all of the people, depending on the sort of way the quantification is going to play out. Okay. And then there's time. So some of the time. Now this one's weirder. Like people are kind of well behaved because, well, people of course are not well behaved as a rule, but in this context, people kind of make sense because people are inherently discrete things, right? So there are currently 17 discrete people in this meeting, Zoom meeting. So I can talk about each of them as individuals. I can be like, there's Alice, there's Nick, there's Kyle, there's Cole, right? Those are individual people, and I could list all 17 of them. Time is sort of weird because time is, at least our perception of time is essentially continuous, right? It flows smoothly and doesn't like come at us in discrete chunks. Now there are moments when we can display or talk about time in that way. So if you have a clock where the second hand, so sometimes the second hand just moves smoothly around and around and around, but sometimes the second hand goes chunk, 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 right? And that would be kind of discrete notions of a second. Or if you have a digital clock of some sort, like most of us do on our computers, for example, then that displays discrete times. It goes from 9:26 to 9:27, like it just clunks over to the next minute as a single discrete action. And so in this context, I need to be able to quantify over time. And so basically, I'm going to talk about a moment in time. So I'm going to imagine, and I'll call that T, and I'll call my person P. So I'm going to imagine time's been somehow cut up into chunks, and I'll be able to talk about individual chunks T, and I'll be able to say, you know, you can fool this person P at that moment T. And that's how I'm going to handle this idea of fooling some of the people some of the time. Okay, does that make sense? Questions about that? Okay, now, so if we have a set of people, so we have P0, P1, P2, and we have moments in time, T0, T1, T2, and if we have our fool thing, if we say, you know, fool PT is true if you can fool person P at time T. Okay. Is all this setup make sense before we come back to the actual statement? Because this setup would apply basically to all 4 parts of 935, including the one that's on the assignment. Questions? Cool. So if we say you can fool some of the people some of the time, and we've got this set of people and this set of times, right? So there's, you know, there's a lot of possible combinations. I can fool P0 at T0. I can fool P0 at P2 at T1, P2 at T1, P2 at T2. So there's lots of possible combinations of P's and T's. And is this, so then the question is this saying for all P's, exist P's, for all T's, or exist T's, right? I've got to quantify over both of those things. And the question is the quantifier over the P's a for all or exists? And is the quantifier over the T's a for all or exists? Okay, those are 2 really central questions to answer, you know, to solve this problem. Okay, so take a second and think about, do you think this is a for all P or an exist P? And do you think this is a for all T or an exist T? And then the third question is, does it matter which order we put them in? And that's perhaps harder, I don't know. So think for a second about that, and then we'll see where we end up. So do we think, let's start with people. Do we think that we're going to have a for all people or an exist people? And why? Anyone?
I think it's going to be an exists.
And
because, well, like some of the people, that's not everyone. That's, you know, some of them. So it'd have to be an exists.
Right. So that makes sense, right? That some of the people suggest that this needs to be an exists. And by the same argument, presumably some of the time means there's probably some kind of exists here. Okay. And so this translates as there exists P, T, and, you know, we could have types and say colon person or colon time, such that we can fool P, T. So this says there is a person and a moment in time where we can fool that person at that time. Doesn't say we can fool that person all the time. Doesn't say we can fool all the people at that time. It just says there is a person and a moment in time where we can fool that person at that moment in time. And that would be our translation of you can fool some of the people some of the time. Now, the one thing about this that people sometimes have questions about, well, I shouldn't say the one thing, a thing people sometimes have questions about is in English, some of the people might often be interpreted as more than just once. Like if I say I can fool some of the people, and it turns out actually I can only fool one person. Some people might be like, well, I don't know, is that some of the people or is that just one person? We're going to take this to mean one or more, and this to mean one or more moment in time, so that the exist works here. If we needed two or more or five or more, whatever, we had some other definition of some, we'd have to update this and it would become more complicated and ugly, frankly. But we're going to take some here to mean one or more. And so this is enough that there is one or more people and one or more moments in time such that we can fool that person at that moment in time. Okay. Questions about that or any of the other exercises from chapter 9? So I'm gonna, I'm going to stop sharing for a second because I want to be able to see the whole thing. We experimented once briefly with putting you all in breakout rooms and having you talk to each other. Did that work okay? Can you like give me a yes or a no over in the participants thing to give me a sense of like, was that a good or clap or some sort of indication of like, did that work for you? Was it a mess?
It worked okay. One part that's kind of hard is like when you're trying to do the problems, you can't really like write together. So you're just trying to like speak the problems.
Right. You end up having to talk, but you don't have, you can't do the right board.
Well, you could, but then you have to kind of try and like write with your mouse and then
which is
like type too.
ugly.
So
right.
Yeah.
Other comments? I mean, so far 3 people have said it was a positive thing. Nobody said it was a negative thing. Okay, then we're gonna do it again. We'll take 3 people as everyone and move forward. So what I'm gonna do actually is there's 5 problems in 9.34. And let me put those up quick on the whiteboard in case that's useful to people. I'm gonna type them because they'll be faster. So this is 9.34 and we have everybody loves somebody. I guess if I make this wider, this will look better. Somebody loves somebody. Everybody loves everybody. Oops, can't spell. Nobody loves everybody. And finally, somebody loves nobody. Okay. So we have these 5 statements, and I'm going to put you in rooms for a little bit. And so the first thing is figure out what the predicate is. You need to have some sort of predicate. What is that going to be? How many arguments is it going to take? What is it going to say? That's sort of central first step. And then once you have that, go ahead and try to translate as many of these as you can. We'll say take, I don't know, 10 minutes. Well, actually, we'll take 5 to 10 minutes. But if your room finishes, you're like, we've done them all. Come back to the main room, and when everybody's back, we can talk. And if there's a room that's taking a while, I might go grab them and pull them back into the main room if we need to. But sort of work on as many of these as you can as a group. I'll put you in groups of like 3 or 4. And then you can see where we end up from there. So does that make sense? Questions before I make room? Zzz. Breakout rooms. So let's see. Oh, there's exactly 16 of you. So we'll do 4 rooms of 4, I think is what we're going to do. So I'm going to make rooms, head off, and when you're done, come back to the main room. Otherwise, at like 9:45, I'll come get everybody and we'll come back into the main room. Okay, questions? Going, gone. Open all rooms. So Justin and Jack haven't joined your room yet?
Sorry, I was outside.
Oh, that's okay. So you should have an invitation to join a room. If you click yes on that, you should just go there.
Yeah, I just.
It's fine. And Jack, do we know what's up? I bet Jack stepped away. Okay. Hmm. Room 4 is back to the first room to return. Oh, it looks like we got another room heading our way. Cool. So 2 room done. Should probably start. Should have like music to play while we're waiting for everybody to come back. And we got a room 1 is still working. We got everybody but room 1. So let me poke room 1. Everyone's back but you. Not where you are. Okay, so hopefully they will be back in a second. Did anybody have any questions about any of that while we're getting our last room back? Oh, here they come. Awesome. Any questions about any of this so far? So I'm going to close all the rooms. And oh, close rooms and go away. There we go. So I think we got everybody. Yes, awesome. So does somebody want to share the predicate your group came up with to capture this?
We just use loves P and Q.
Okay. That seems entirely reasonable. So we're saying P loves Q, presumably.
Right.
Awesome. So then group one, actually I'll just do, I'll pick on different rooms. So room one, do you have somebody have a suggestion as to how we might do A? Probably should have had each room nominate a reporter, but didn't do that. So
I don't
somebody
remember
from room
which
one.
room I was in.
Oh, and now I don't even know.
Yeah, I also don't know what room I was in either.
Well, then I clearly thank you for saying that. I didn't actually think about that fact, but of course there's no reason you would have paid any attention to what room number you were in. And I don't have that information, I don't think, anymore. So let's just have people volunteer. So if somebody
Well-
want to volunteer a solution to A.
For us, we did for all P exists Q.
Okay. So for all P exists Q loves PQ. So we're saying every person has the property that there is someone that they love. So everybody loves somebody. That seems reasonable to me. Are there questions about A from anybody? Is that, did a group come up with something different than that? Okay. So somebody that was not in Justin's group, so Justin let his whole group off the hook there by volunteering. Somebody that wasn't in Justin's group want to tell us what your group came up with for B?
For B, we did pretty much the same thing as A, except we replaced the for all P with an exist P.
Okay. So there is a P and there is a Q where loves PQ. So somebody loves somebody. And we could write this, that was a terrible paren, because these are the same quantifiers, it would be also legal to do this. And probably slightly shorter. So either of these, they mean the same thing and they would be fine. Okay. Questions on B? Then how about C? Somebody who was not in Justin's room or Josh's room. And now you may not even remember who is in your room, but let's hope that you can remember that you weren't with one of them.
Both would be for all.
Okay. So for all P, for all Q, loves PQ. And again, we could just do a single quantifier because the two quantifiers are the same. Yeah. So every person loves every person. So everybody loves everybody. For all people, P and Q, P loves Q. Questions about that? Then somebody wanna, so there's probably one room we haven't heard from. Does somebody from that room wanna provide an answer for D? Just somebody we haven't heard from, like ignore the rooms because you may not even remember what room you're in, but somebody we haven't heard from want to provide an answer from D?
Yeah.
Sure.
So we had there's not exists.
So a negation.
Yeah.
Okay.
P for all Q loves PQ.
Gotcha. So there is no person that loves everybody. So nobody, no person loves everybody. So that's totally reasonable. Now, because of generalized De Morgan, right, there are ways we could rewrite this that would be equivalent. So we could push, the negation in. Oops, there should be a colon here, and here, and here, and here. And then we could say not for all Q loves PQ. So everybody doesn't love everybody, which doesn't seem obviously the same, but generalized De Morgan says that it is. And then we can push that in again, and we can have for all P exists Q not loves PQ. So this says for every person, there's somebody they don't love, which is a little more, for me, maybe a little better connected to this. How would we show that nobody loves everybody? We could show that for everybody, there is somebody that they don't love. So this would be a way we could sort of prove that D is true. So this first one, I think, is the right answer to the translation problem. But it's interesting to see that there are these logically equivalent statements that we know are equivalent by generalized De Morgan, but which don't really translate in the same way. Like they don't feel the same in some ways. Questions about that? And then does anybody want to share an answer to E? Open to the floor. Could even be somebody who's already spoken, just to move this train along.
I put exists P for all Q not loves PQ.
All Q not loves PQ. Yeah, so there is a person that doesn't love everyone. So, which would be the same as saying loves nobody. So that seems like a totally reasonable solution to me. So questions about any of these? Did any group have something different that you want to ask about or put up here as a comparison point? So at this point, if there aren't any questions, I'm sort of done with chapter 9, and I will move on to chapter 12. So we're about to leap off to some totally new material. So if you got questions about anything from chapter 9 or earlier, now's a great time to ask.
I guess I have a question on D.
Yep.
So like in the first part, we have like not EP.
Mm-hmm.
Could you replace the E with the for all and leave the negation out in front?
No, because that would be, if you have so here, you're suggesting as an alternative for D, not for all P, for all Q, loves PQ. Now, this is saying that it's not true that everybody loves everybody. And because we took this to be this piece right here, right? So this is everybody loves everybody. We're saying it's not the case that everybody loves everybody. And there are different ways that could not be true. One of them could be that nobody loves everybody, but it might be that some people love everybody, but not everyone loves everybody. And if that was true, this could be false, but that might also not be true. Okay. So negating this is too strong. It basically says that, let's see, or too weak, I think. This would say, if it's not true that everybody loves everybody, if there's any pair P and Q where P does not love Q, that would negate this. So if we imagine, let's have a simple universe where there's like 5 people, and we'll have an edge between them if P loves Q. If we have the for all, we're saying every edge exists. Okay, that would be every P loves every Q. So the negation of this would be erasing any edge would be enough to make that not true anymore. So that is now a negation of this. But that's not, that doesn't satisfy D. It's not true that nobody loves everybody, because we still have people here that do love everybody. So this node has an edge to all 4 other people. So this individual loves everybody in this very small universe. So we've made C false, but we haven't made D true. Does that make sense?
Yeah, that makes sense.
Yeah. So we need, for D, we need some node that doesn't connect to everyone. So there is a P that doesn't connect to all of the Q. And so we're going to need some node that doesn't love everybody. We need that there is no node that loves everybody. And right now there's 1, 2, 3 that still love everybody. So we'd have to remove some more edges. Like we could erase this edge, and then we could erase that edge, and we could erase this edge. And now nobody has 4 edges coming out of that node. And so we know that nobody here loves everybody. Nobody loves more than 2 people now, actually, in the version that I made by erasing those edges. So that's a great question. Other questions? Going on. Okay. So let's make a new page. So at this point, we're going to start talking about chapter 12. So we're jumping over chapters 10 and 11, which I'll explain here in a second. So chapter 10 is actually pretty important, and we're going to definitely come back to chapter 10. Chapter 10 is where we talk about proving the correctness of programs. And so it's really pretty critical. The authors of the book choose, and I understand why they did it, but they choose to sort of split the program correctness stuff into 2 pieces. Part of it's in chapter 10, and the other part's at the end of chapter 11. And I find that sort of, when I've taught this class in the past, I find that sort of odd, and students are sometimes confused. And so what I'm going to do instead is do the beginning of chapter 12 now. Then we'll come back to chapter 10 and do chapter 10 and the end of chapter 12 all in one sort of piece on program correctness. If there's time, we might return to chapter 11. We're running slower than normal, and that's fine. I am not in any way criticizing. It's a weird time. I think it's kind of amazing that we're kind of making as much progress as we are, and that, you know, you're still showing up at 9:15 in the morning to watch me on television, which seems frankly kind of nuts. And so if we don't get back to chapter 11, I'm okay with that. We'll see kind of what happens, but I may manipulate the end of the schedule depending on how long we spend on 12 and 10. And we might come to 11, we might do something different instead, but we'll be sort of flexible about that. So chapter 12 is about a proof technique called induction. And what the heck is that? Well, there's actually, now that we've introduced quantifiers, we have a complicated problem. If I want to prove something about a finite, discrete set of things, I can do that by just checking all of them. So if I want to say everyone in the class has a nickel, I can just go through and ask each of you individually if you have a nickel. There's only 16 of you. It'd be tedious, but it's entirely doable. I can check every one of you and say, do you have a nickel? Do you have a nickel? Do you have a nickel? And then I would be done, okay? But there are things we want to say that involve infinite sets. And then this idea of I'm going to check every one of them becomes infeasible. So as an example, I might want to say, for all I in the integers, and remember that's both positive and negative, I want to say that I squared is greater than or equal to 0. Okay, that's a true statement, right? If we square things, we get positive values or non-zero values. If I is 0, it might be I squared is 0, but everything else is bigger than 0. So this is a true statement, but notice it's an infinite number of statements, right? I'm saying 0 squared is at least 0. I'm saying 1 squared is at least 0. I'm saying -1 squared is at least 0. I'm saying 2 squared is at least 0. -2 squared is at least 0. Right? 8,000, oops, that was a terrible 8. 8,427 squared is at least 0, right? So I'm saying an infinite number of things here. And so if I'm like, you know, if I claim that I squared is greater than or equal to 0 for all integers, and you're like, prove it, it's not a very good technique for me to say, well, let me list them all and show you that each one is greater than or equal to 0, right? That is gonna not be feasible because it would take an infinite amount of time. And I don't have an infinite amount of time to do it, and you don't have an infinite amount of time to check it. So not a win. We can't do that. So this is actually a pretty fundamental problem. And this was observed several hundred years ago in mathematics. It was not really cleaned up terribly well for a long time. There was a lot of sort of hand-wavy, well, yeah, but you know, it kind of works kinds of answers. And then there was sort of a good, clean solution to this introduced called induction. And that's what we're going to talk about in chapter 12 is induction is a proof tool that lets us prove these kind of infinite sets of statements, okay? And so it's a proof rule for infinite sets of statements. And it's a little weird in that we don't prove all of the statements. We can't really. you can't, because there's an infinite number of them. But we provide a mechanism for generating, a proof for any one of them kind of on demand. So we're not going to prove all of the infinite number of things because we can't. We don't have enough time. But what we'll do is provide a mechanism where if you come to me and you say, okay, show that it's true for I equals minus 3,229, I'll be like, no problem, I've got a way to do that. And I could do that proof for you. That would be a single finite proof, and I could do it. And you could be like, oh, okay, great, that worked. Well, how about positive 11,422? And I'd be like, I got a plan for that one too, and I could do it. And so for any number you give me, I can give you a proof, a finite proof, but I'm never going to give you all of the proofs. I will just be able to give you any individual proof if you ask for it. And the idea there is that if I can do it for any number you ask about, that means it must be true for all of the numbers, because there's not a number that I won't be able to not prove it for, right? Since I'd be able to do it for any given number that you ask about, we'll just take it as great. That's enough to show that it's true for all of the numbers, okay? Does that make sense? At least in vague, kind of like whatever Nick says, yeah, sure, fine, kind of land. So how does this work? Oh, thank you, Cole. How does this work? So the basic, there's actually 3 different mathematical induction axioms in the book. Well, actually, the first one's an axiom, and the other 2 are technically theorems. 12.3, 12.4, and 12.5. I'm actually going to start with 12.5 because I have found that that is easier for students to think about sometimes than the others. And so I'm going to start with the third one, and then we'll clean up and talk about the first 2. And, you know, it's 10:12 right now. So basically, I'm going to sketch something in the next few minutes. It'll be pretty loose. And then you'll all get to sleep on it over the weekend. And I'm sure you'll think very hard about it because you have nothing else to do this weekend but read the beginning of chapter 12 and think about this. And then we'll come back Monday. And I was joking, of course. We'll come back Monday and we'll kind of pick up at the beginning of induction again on Monday. But the basic idea is, if you imagine that you've got a set of stepping stones, and maybe it's an infinite set of stepping stones. So we've got some infinite sequence of stepping stones. And this is stone 0 and stone 1 and stone 2 and stone 3, 4, 5, 6, 7, 8, 9. And we want to prove something is true for everything, every position. So we want to prove P of 0, and we want to prove P of 1, and we want to prove P of 2, and P of 3, and P of 4, and etc. So we want to prove something is true about all the natural numbers, okay? So we have this infinite set of numbers, and we want to prove that something's true about all of them. Like maybe that I squared is at least 0. Now, we can't prove this infinite set of things. So what we're going to do instead is we're going to prove P of 0. And this is called the base case. And so that is that guy right there. So we're going to prove P of 0. In some sense, we're giving ourselves an ability to get onto the first stepping stone. If we think of this as sort of a sequence of stepping stones, proving P0 allows us to get onto the first stone. Okay? Now, then the weird part, so the induction step, and this is the part that really tends to confuse people, is we're going to prove that Pn, should I do this right? Implies Pn plus 1. So we're going to, and this is actually going to be a for all. So we're really going to do for all let's say for all n in the natural numbers, P of n implies P of n plus 1. So what is this saying and why do we care? This basically says if we know that it's true for P of 3, then, because it's for all n, we also know it's true for P of 4. So we can make the leap from this stone to that stone. And we can also make the leap from 6 to 7 and 9 to 10. And in fact, like because this is for all n, well, we can also go from 0 to 1 and 1 to 2 and 2 to 3 and 4 to 5 and 5 to 6 and 7 to 8 and 8 to 9. So we can do any adjacent pair that we want. And this allows us to, P0 allows us to start. And the induction step says that, well, if I can start, I can go from there to anywhere by repeating this n to n plus 1 step over and over and over again enough times. So if you say, well, prove P of 8, I can be like, great, I can prove P of 0. And I know that if P of 0 is true, then P of 1 is true. So now I'm here. And I know that if P of 1 is true, P of 2 is true, and I'm here. And then I can go here and here and here and here and here until I get to 8. And so I could unwind this into the base case plus some finite, possibly very, very big, but some finite set of steps of this form, and I can get to whatever number you ask me for. So if you say, prove it's true for 1,000,000, I could be like, I can do that. It's going to be really, really slow and tedious, and you don't really want to watch me do it, but I can do it if you insist. And I can start at 0 and go to 1 and 1 and go to 2 and 2 to 3 and 3 to 4, blah, 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 out to 1,000,000. And I would have proven by basically transitivity that 1,000,000 is true because 1 was true and 1 implies, or 0 is true and 0 implies 1. So that means 1 is true and 1 implies 2. Well, that means 2 is true, blah, 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 all the way out. And so for any finite value, I can construct a proof, a sequence of steps that would get us from 0 to that finite value. Okay? That's sort of the central piece of induction, is that we can get anywhere through enough little steps. Okay? Questions about the general setup? That's usually fairly baffling. So feel free to holler. So we'll look at examples of this on Monday, and then we'll unwind the other 2 versions on Monday and talk about what all these things are saying. But this is the basic idea. And so while everybody often finds the idea of induction kind of overwhelming, the proofs are not that complicated and they're pretty mechanical. You do two things. First, you prove the base case, and then you approve the induction step. You assume that P of n is true, and you show that P of n plus 1 is true. And so doing an induction proof is usually just a matter of doing the base case, which is typically a very simple proof because you plug in 0 and it turns out everything collapses. And then you do this step, and that's often not too bad and tends to use a split off term from 8.23 a lot. Not always, but it frequently uses split off term. So we'll look at how that plays out when we get some examples. So are there questions about any of this? Class officially just ended as all my devices went ding. Questions quick before we wrap up? Awesome. You rock. Thank you very much. I will see everybody on Monday. I did record this. Yay! And so I will get this posted today and have a look and let me know if you get any questions. See everybody later. Ciao.